So our last skill in this unit on properties of mixtures, thinking about solutions and colligative properties, is the quantitative piece of colligative properties. This is what your in-person quiz is going to be about. We've got 4 different kinds of colligative properties that we've talked about, so 4 different kinds of calculations that you need to do. So thinking about this builds on everything that we've talked about in our previous skills, because the first part of doing a colligative property calculation is knowing or determining the concentration of solution that you're working with. So that was what our previous skill was about, thinking about molarity, molality, mole fraction. Okay, those are going to be the 3 main ones that we're going to talk about with colligative properties. And I know this looks like a giant alphabet soup right here, but these are the different colligative property equations that will be provided for you, but you need to know which one you're going to need to use. So just as a heads up, this is the one for boiling point elevation. This is the one for freezing point depression. Either one of these could be used for vapor pressure lowering, and this is the one for osmotic pressure generation. So you need to know which one to use, and I'm going to explain those on the next few slides. All right, vapor pressure actually has 2 different calculations or equations that you could use. This first one is what we call Raoult's law, and it's going to calculate a new vapor pressure for us. The new vapor pressure, notice the main difference here is we don't have anything there. This little circle here tells us that that's for pure solvent. This is the vapor pressure of solvent when there is solute present. Okay? So in words, what is this equation telling us? It's telling us that the actual vapor pressure of the solvent is going to be scaled down from our pure value by whatever the mole fraction of solvent that we have. And I know sometimes looking at equations can be kind of crazy. So let's see if we can make sense out of this. What's going to happen? We talked about vapor pressure lowering. So this fraction is always going to be, let's say, between 0 and 1. We're talking about the mole fraction of solvent. If the mole fraction of solvent is 1, that means there's no solute. There's no scaling down. As this mole fraction becomes less and less, because we've added more and more solute, that means the vapor pressure of the solvent in that solution is going to become less and less. So this is a scale down factor that we're going to see. Okay? So that's one way we can think about. This will give us the absolute value of whatever that new vapor pressure is. I'm going to show you another equation that you can use, and you have to make sure you pick the equation that's answering the question that it's asking. Is it asking what's the new vapor pressure, or is it asking how much is the vapor pressure being lowered? If it's asking how much the vapor pressure is being lowered, we need to use this equation. This is going to tell us how much it's being lowered, the change, this triangle, this is delta, that tells us the change in the vapor pressure, how much it's being decreased. And notice here we're using the mole fraction of solute. This was mole fraction of solvent. This was mole fraction of solute. Now let's think about this. This mole fraction can also run between 0 and 1. Let's imagine that we've got a pure solution of solvent. Well, that means that the mole fraction of solute is going to be 0. That means there's no vapor pressure lowering, which makes sense, right? We've got no solute in there to do any lowering. So both of these equations will allow us to think about the depression and the lowering of vapor pressure. But again, use the equation that allows you to think of the amount of change or the new vapor pressure. Okay? Now, what if you use the wrong calculation? So this little slide here is going to show us that these 2 equations are related, right? Because the change in vapor pressure is really whatever the vapor pressure was in the pure situation and subtracting what it is now. So if you accidentally use the wrong equation, and this equation will be provided as well, you can remedy it by using this equation to solve for the piece that you need. But vapor pressure, you have to make sure you're answering the question. Is it asking for the new vapor pressure or how much it was lowered? Okay? All right, boiling point elevation. So that's this guy. Okay, in words, again, looking at these equations, what do they mean? Well, this tells us that the magnitude of the boiling point elevation, so this is going to tell us how much the boiling point is increasing. Keep in mind, if you want to know what's the new boiling point, you need to add this to the pure boiling point. Again, think about and find out what the question is asking. Is it asking how much the boiling point will be elevated, or is it asking what the new boiling point will be? They're two different questions. We have to make sure that we answer it correctly. But this, again, is scaled by and proportional to how much of the solute we have. So this is the molality of the solvent, and then a constant. Okay, so these again are directly proportional. If we increase the amount of solute we have, we're going to have a greater boiling point elevation. Okay, so note that this equation gives us amount of change. Maybe that's what the problem is asking. But if it's asking for the new boiling point, you need to take this answer and add it to whatever the boiling point was. I'm going to assume that you know that the boiling point of water is 100 degrees C. If we have another solvent, I will make sure to provide that new boiling point for you that you'd need to add this delta T to. Okay, and again, this is a constant that would be provided for you as well, but you might need to be doing a little bit of work to calculate the molality. All right, freezing point depression, very similar, except in this case, we're talking about how much we're lowering the freezing point. So again, this is going to tell us the magnitude of the change that we're going to have in the freezing point from pure solvent to when we have the solution. Maybe that's the answer to the question, but if you want to know what the new freezing point is, you need to subtract this value from the freezing point of the pure solvent. Okay? Again, we're going to use molality for our concentration here, and there's going to be a constant that we'll use as well. Highlighting, just like for freezing or for boiling point elevation, this equation gives us the amount of change. You may need to subtract that from whatever the freezing point is of your solvent. If we're talking about water, I'm going to assume that you know the freezing point for water is 0 degrees C. Other substances, I'll provide that value for you. All right, the last one is osmotic pressure generation. In reality, we're not going to see or do a ton of calculations with this, okay? But this is the equation for osmotic pressure generation, okay? This pi is that osmotic pressure. We're going to use molarity, the gas constant, and then temperature. Okay, so these are going to be the pieces of information that we'll use to calculate what is the osmotic pressure that's generated. So again, the magnitude of the osmotic pressure depends on the temperature of the solution, okay, how much of the solution there is, and this is sort of reminiscent. Remember our PV equals nRT? We can rearrange PV equals nRT so it looks like this. P equals N over V times RT. N is moles, V is liters, volume in liters. That's molarity. So this is related to this equation. Okay, one last little thing to highlight here. All right, so we've done all this. We calculated our concentrations with the right units. We used the right equation to do our colligative property calculation. Well, there's one last little thing to think about, and that is that all particles are not created equal. Right? So we're going to see in the equations that you get, there's going to be a little I value that's there. Well, what do you mean? Well, I've been talking about salt and sugar this whole unit, and now it really comes into play in terms of how we think about calculations. Okay? So again, when we think about salt here, when we think about salt, we're going to have that dissociate into particles. So if we've got 1 mole of sodium chloride, this dissociates into 2 moles of particles, right? And if you need to go back and review that from Gen Chem 1, when we've got sodium chloride, let's go ahead and write it up on top here. Sodium chloride is going to dissociate into sodium cations and chloride anions, okay? When we've got sugar, 1 mole of sugar dissolves into 1 mole of sugar particles. We don't get more particles because we don't break apart sugar. So that's really, really important to understand that. And what this means is ionic compounds have a little bit more strength when we think about their ability to manipulate colligative properties. Okay, this is why you don't throw sugar out on your walk, right? When you want to melt the snow, okay, you put a salt out there because you get more particles, and so that's going to have a greater effect on colligative properties. So how does this sort of manifest itself? Don't worry about the name, but we create what are called Van Hauf factors. These are scaling factors. The values of I go between 1 and they loosely equate to the number of particles that you have. So this tells you the number of particles. If you're just generating one particle, then the equation doesn't matter with that I. But if it's table salt and you've got 2 particles, or magnesium chloride, MgCl2, that makes 3 particles, or aluminum chloride, AlCl3, that makes 4 particles. That makes those salts 2, 3, and 4 times more powerful with their vapor pressure lowering, their osmotic pressure generation, their freezing point depression, or their boiling point elevation. So we need to be able to think about how many particles we're making, because that's going to affect our colligative property calculations. So just to highlight, these are the equations that will actually show up on your equation sheet with these I values. Again, if you've got a covalent compound, it's not going to matter. But if you have an ionic compound, you need to count the number of ions that you have and use that for your I value. All right, that's it on colligative properties.